Welcome back to Blemmings Labs. It's my absolute delight to introduce our next speaker, Peter Chubb. Peter's going to be talking to us about performance, and it's not down in the noise. Peter's been using or contributing to the Unix and Linux systems since 1979. He currently works with the Trustworthy Systems Group in Data61, CSIRO. Peter's expertise is in Linux kernel and low-level system software and in measuring and improving these. So just a quick reminder, please use the questions tab in the chat channel for this room in Venulus. And if you have any issues there, please chat to Stephen, who's the moderator for this discussion. See you after for Q&A. Thanks. Please take it away, Peter.
Okay. This all started some time ago when I fed up with seeing on mailing lists when people say, oh, we've got this new feature, or I've made these changes to the code. And the performance difference is just down in the noise. When I look at it, there ought to be a performance difference. And I'm here to say that it's not down in the noise. If you think it is, it's probably because you don't know yet how to use statistical tests to tell you whether it's down in the noise or not. Before going on to my first real slide, I'd like to acknowledge the traditional owners of the land that I'm living in, the Gadigal people of the Eora Nation, and pay my respects to elders past, present, and emerging. I'd also like to say before I really go on that I'm not a statistician. Most of the stuff that I'm doing is empirical. And if you've got any real statisticians out there in the audience, try not to wince too badly, please. I'm also going to try and start just with high school maths and not go beyond anything you didn't learn and have forgotten since year 10. So what did you learn back in year 10? Well, you probably learned about minimum and maximum. You know, the minimum is the smallest in your measurement set. The maximum is the largest. The mode is the most common value. The median is the one in the middle. And the mean, well, means what you get when you add them all together and divide by the number of things. And what does that actually mean? What does the mean mean? I'm going to spend a little bit of time trying to talk about what the mean actually means and whether it's the right measure for you. Depending on which school and which courses you did, you may also have covered variance and standard deviation. I'm going to talk about those too. There are also tests for significance, Z-test, student t-test, chi-squared. I covered those in biology in year 10, not in maths, and I still don't really understand them. So I try to use them, but I'm never quite sure whether they really mean what I expect them to mean. I'm not really going to cover them today. What I am going to cover is the U-test, which is a very simple test to say whether two measurement sets are the same or one's better than the other, that I believe I can explain to you with only high school maths. That's good. As you know, the first thing you do to a measurement is repeat it, because you might measure 57 once, but the next time you measure it's 60 or 58 or whatever, and you just keep on going on. What's the true value there? Well, there's two different cases that you might be measuring. You might be measuring a value and there are random errors, the noise, or it might be that you're sampling a population where the things you're measuring are actually different each time you measure them. So in the first case, you're trying to measure a length or something. Measure the length of, the other thing I had to do the other day, measure the inside diameter of my clarinet. And every time I measured, it was half a millimeter different. Or you could be sampling a population. So you want to find out how tall people are. And some people are taller than others. I'm going to concentrate for now on measuring a single value. If you've got some true value V that you're measuring, then each measurement that you measure is that value V plus some error. I'm saying epsilon I is the error in the ith measurements. That's the noise. If you've got truly random measurements, they're going to be normally distributed around 0. So it's equally likely you're going to have a negative error or a positive error. And that means that if you add all the errors together, it's going to go to 0 as you increase the number of measurements to infinity. So up on the right there, you've got the formula for mean. I don't know whether you can see my, no you can't, okay. You just add all the values together and divide by n. What you're doing there is adding up all the actual value plus all the errors and dividing by n. And that gives you an approximation to the real value as you increase the numbers as you increase the number of measurements. That only works if your noise is randomly distributed about 0, so you're equally likely to get a positive and a negative value. You also want to know, are your errors broad? So have you got lots of errors? Is it wide, or is it very, very narrow? If you just add up the errors and average them, you're going to get something that's close to 0, which is what I just told you. So instead, we're going to add up the squares of the errors, and that gives you the variance, sigma squared. It's the sum of all the errors, or the squares of all the errors. You can think of each error, if they're truly independent, as being orthogonal on an orthogonal axis. So the measure you want for the total error is kind of Pythagoras, and that gives you the standard deviation. It's the square root of the sum of the squares divided by the number of measurements. This standard deviation, we don't normally know what the errors are because we don't know the true value of V. So we usually approximate each error being the measurement minus the mean, which is the estimate of the value that we've got. That makes things a bit difficult, and you've got to do some more statistics. So yeah, before I talk about that, I want to talk about one other thing, which is the standard error on the mean. Why did we divide by n instead of n squared in that thing? If you divide by n squared instead, you get what's called the standard error on the mean, which is normally written as sigma divided by the square root of n. This is exactly equivalent, as far as I'm concerned, to the standard deviation. It's just a different way of expressing the same thing. Statisticians will differ and say that it's got a slightly different meaning, but for practical purposes, when you're reporting a measurement, they're the same. This means that when you're actually reporting a measurement, you should always give either the standard deviation or the standard error and say the number of measurements taken, because that way people can move to whichever of the two standards they want. So you can express it as 10.5 plus or minus 0.04, and that means that the mean of the value you're measuring is 10.5, and the standard error on the mean is 0.04. Alternatively, you can express it as a standard deviation plus a mean. I normally put the standard deviation in parentheses, and you count from the right for significant figures. So in this case, we've got 10.50, that's 2 decimal places, and the 20 are the two right, correspond to the two rightmost significant figures of the mean. So the mean here is 10.5, and the standard deviation is 0.20 to two significant figures. If you've got exactly 25 samples, these are equivalent, because 0.2 divided by the square root of 25 is 0.04. If you've got a normal distribution, that is the bell curve, you can think of that in two ways. It can either be a histogram of a population, or it's the probability that the true value is within a particular range. 68% of the population that you're measuring is going to be within one standard deviation. 95% of the population is going to be within 2 standard deviations, and 98% within 3 standard deviations. You also note that the mean and the mode and the median are all the same for a normal distribution. You can also think this as the probability that the true value measured is in that range. So it's a 68% chance that the true value you're measuring is within 1 standard deviation of the mean. It's 95% likely that the true value is within 2 standard deviations of the mean, and it's 98% likely that it's within 3 standard deviations of the mean. If the samples are normally distributed, you can compare 2 measurement sets using chi-squared or student's t or z-test. You're not expected to understand this because I don't. If the distribution isn't quite normal, you can use the central limit theorem, which I'll come to in the next slide. And if you use a test that's robust to non-normality, then if it's just a little non-normal, that is, it's sort of bell-shaped but isn't actually normal, you can still use the test. Both students T and Z test are meant to be robust to non-normality. Chi-squared, I believe, is not, but I'm not sure about that, so don't quote me. The central limit theorem, according to Wikipedia, says when independent random variables are added, their properly normalized sum tends towards a normal distribution. I don't know what that means, so I've got my own version. If when you make your measurements, the histogram looks roughly normal, and you take enough measurements, you can pretend it's normal for the purpose of taking mean and standard deviation and using students' t-test or z-test. Let's have a look at a real kernel benchmark. This is the time to execute clock get time with a real-time clock. We have a mean of 59 cycles with a standard deviation of 16. The mode is 60 cycles and 56% of the samples hit the mode. The minimum is 52 cycles, the median is 60, but the maximum is greater than 2000 cycles, which is where I stop measuring. And that's for 10 to the 8th tests. There's something slightly off here anyway. I was expecting the minimum to equal the mode, and it doesn't. And I suspect that's because of the way I'm measuring it. What's clear here, though, this is nowhere near a normal distribution. The minimum is very near the mode. The mode is equal to the median. It's got a huge tail, and some samples are greater than 2000 cycles. This is, if you zoom in, you can see that it's got oodles of minor modes. So there's a mode around about 60 cycles. There's another one around about 150, another one just under 250, and another one just under 300, all with different proportions of the measurements hitting it. Given that it's not a normal distribution, what does it mean to say that the value of the time it takes is 59 cycles or whatever? We're going to have to come up with a different measure. And if you're going to try and compare this with another sample, you've got to do something different. So because this isn't a normal distribution, you can't rely on the 68, 95, 98 rule. You can't use the Z or the T tests, and the mean may not be the best measure of what the value actually is. So what I'm going to do is I'm going to change something. I'm going to make a small change in the kernel that I expect will lead to a change in the time that this operation takes. We've got 10 to the 8th tests here. On the left-hand side one, it's the one we just saw with a mean of 59 and a mode of 60. On the right hand, we've got a mean of 58 and a mode of 58. The standard deviation on both of them is fairly large. And if you just use students' t-test, which is totally meaningless in this case, it says accept the null hypothesis that they're the same. I expect them to be different. We need a different test. So I was really, really happy about May last year to discover this thing called the Mann-Whitney U test. What we're going to do here is we've got two sets of measurements, before and after, A and B. We're going to pair each measurement in set A with every measurement in set B, just like a cross product. And then we're going to compare them. Did the measurement in set A beat the measurement in set B? Did it draw or did it lose? And for each measurement, for each contest, we're going to count. We're going to count 1 for a win, half for a draw, and 0 for a loss. Add them all up and divide by the number of contests, where the number of contests is the number of measurements in the A set and the number of measurements in the B set. I'll give you an example. In this case, sets A and B are identical. We can think of this as the number of seconds to do something. So B takes 1 second, then 1 second in the next measurement, 2 seconds in the third measurement, and 3 seconds in the fourth measurement. And likewise for A. I'm going to consider it from A's point of view. A draws with B in the first two columns and wins in the second two columns. Same in the second one because it's still the same value. In the third column, first two measurements, draws in the third and wins in the fourth. And likewise in there. So if you add them all up, we've got 6 draws, 5 wins, and 16 contests. So we get a U statistic of 0.5. 0.5 means one is exactly as good as the other. If I make it so that the set A is slightly better in one case, we get an extra win there as opposed to a draw. And if we measure it out, we get 0.56. which is slightly better. If you look at a formal meaning of this, U is a likelihood that running on system A will be faster than running on system B. Formally, it's the probability that A beats B plus half the probability that A ties with B. And the really nice thing is that you can use it wherever you have values that you can compare. And it's really easy to understand what you're doing. A beats B more often than B beats A. You've got a number higher than half. If B beats A more often than A beats B, then you're going to get a number less than a half. Simple, eh? So let's look at these things. This time I get a U of 0.76. There's a real difference here. B, the second one beats the first one a lot of time. What's going on here? Well, this is a very, very common situation in kernel code. Most of the calls hit a fast path, but sometimes it uses a slow path. And sometimes the kernel does other stuff. The other stuff is noise, but whether it hits a fast path or a slow path is part of your measurement. The other stuff that you're doing there, the noise, will tend to cancel out in the U-test. But the change from using fast path to slow path is going to be the thing that the U-test measures. There's also a bit of phase noise because I measured this using the TSC, and on a modern Intel processor, the timestamp counter runs asynchronously to the CPU clock. So you get a bit of phase noise and off by 1, and that's why the minimum is not equal to the mode. It should be. So let's have a look at the internals of clock get time. Clock get time is very, very highly optimized because it's often used for benchmarking things and for timing stuff in the when you're doing other benchmarks. So you try and make it run as quickly as possible. 60 cycles corresponds to about 13 nanoseconds on my system. So what it does is the kernel maintains a chunk of variables, secs, nsec. That's the seconds and nanoseconds at the last time when the kernel was sure of the time. And the last timestamp counter, which was the value of the timestamp counter at the time those were valid. It also maintains a slope as two variables, a slope numerator and a denominator. I'm simplifying a lot here for people who are familiar with the timestamp code and the time measurement code for the purpose of making things easy to understand. There's all sorts of stuff about per processor and so forth as well, which I'm not going to go into. Anyway, you've got these things, and then what clock get time does is look at these, which are mapped into a page that's common to the process, into the VDSO. It reads its own cycle count, subtracts the last timestamp counter, converts that to nanoseconds by multiplying by the slope and dividing by the denominator of the slope, works out what the value, a time value is by setting up seconds and nanoseconds. Because nanoseconds might have overflowed now, it'll call normalize and return it. In the meantime, the kernel might be updating this stuff. So all of that code is surrounded by a sequence lock. The way that a sequence lock works is that if there's no contention, it'll run through the code on the left really, really fast. So it'll grab a copy of the sequence lock. If it's even, we'll just run straight through with a memory barrier to make sure we've got all the values correct. We'll grab a consistent value of the variables, and then we'll compare to make sure that the last sequence that we saw hasn't changed in the meantime, and calculate a time from a copy. At the same time, writers, like the tick that happens every now and then, and the network time protocol called edge time every now and then to adjust the slope, or to step the time, it uses a spin lock so that writers get protected against other writers. It ups the sequence, does a write memory barrier to make sure that's visible, and then it updates the variables. It tries to keep that update variable things really, really short. It actually calculates everything offline and then just does a copy and blats them all in. and then increments the sequence again. So it starts off with the sequence even. It comes in increment sets of the sequence now odd, which means that if clock get time hits during this period, it'll spin in that first little bit, the do last sequence equals sequence while last sequence M1. But if there's a different interleaving, it'll get caught by the last sequence not equal to sequence and boot again. That's what causes those other modes in the graph. I promised I'd tell you what the actual change was. Well, I changed the value of Hertz. I've turned off dyne ticks for the purpose of this demo, and I changed Hertz from 1000 to 100. That means that slow path should be hit 10 times less often. The other noise is still random and doesn't hit the results. So I expect there to be a change, that we hit the slow path less often, and we saw that. We got a 0.75, 0.76 for the U test. What this means that we need to find a different way of measuring and saying what the time is, and maybe the mode is the right one to use. I don't know. The nice things about the U test is it can be used anywhere. It doesn't depend on whether the distribution is normal or whatever else. It could be anything you like. It's really understandable, and it tells you if a change is real. It's even understandable by me. The problem is that it tells you the change is real, but it doesn't tell you what the magnitude is. You've got to use a different test for that. But at least you can say there is a change. It's not down in the noise. For comparison, if I try 2 measurement runs with the same value of Hertz, I expect the value of U to be constant, right? So here's 2 values, both with Hertz equals 100. We've got a different mean. The standard deviation is such that these could be the same. When I do the U test, it comes out as 0.50, which says there's no real difference. That's really good. So it actually works to show that things are the same or things not the same. Let's do another comparison. I'm going to choose another operation that's a lot noisier than clock get time because it hasn't been as highly optimized. And what I'm going to do is I'm going to kill my parent with signal 0. So I've already done a get peeped outside the loop for measuring. This is another case where we've got a fast path and a couple of slow paths. The mean is different in the 2. But if I do this U test, I get 0.49. Is that 0.5? Is 0.549 near enough to 0.5 to say they're the same? Well, U is a measurement. Let's repeat it. So what I did was I took more pairs of tests. I ran the 100 Hertz and the 1000 Hertz versions 4 times each, and then calculated the mean of the U test. It is the case that the U test is supposed to be normally distributed about the mean, which means we can use the student T on this and accept the null hypothesis at a 99% confidence. The null hypothesis in this case is that U is 0.5. So we can show that those 2 tests are actually the same, even though they don't look the same, and without using any complicated mathematics. I think that's really cool. Yeah. So in summary, when you're making your tests, first you try and reduce noise. You try and remove all things from your system that are not likely to be important for your measurements. So turn off SMP, run with max CPUs equals 1. Turn off your network, turn off all your background tasks, run in single user mode. Repeat your measurements often. There's a rule of thumb which says that means aren't valid with fewer than 50 measurements, but it's going to depend on your measurement and what your standard deviation actually is. Understand your system. Fast path, slow path is a really, really common pattern. And maybe you need to use outlier elimination or something more sophisticated to find individual modes and measure each of them separately. And please, please, please give enough information for people to understand your results. Just quoting a mean isn't very helpful if you don't know what the underlying distribution is. And use appropriate statistical tests. I've got a question. Is there an assumption that the U test that only one thing has changed? No, there isn't. You can change as many things as you want, but it will make it harder for you to interpret your results. If you only change one thing at a time, then it's much easier to see what the effect of that one thing is. Of course, sometimes you're actually trying to measure confounding changes so that two things changing together have an effect. The other thing is that you've got to be careful to, very careful to keep your measurements independent. So reboot between tests, because otherwise page coloring is going to get in your way. Try and drop caches if you're not going to reboot, and so on and so on. Use your appropriate statistical tests. And to leave you with something, benchmarking is hard to do anyway. Meaningful benchmarking is even harder. But now I've taught you about the U-test, use it. That's the end of my prepared talk. It went faster than I was expecting and faster than my dry run. So I'm happy to take questions. I can't hear you, Pev. I think you're muted.
Apologies. Thank you. Thank you so much. That was a really great talk. And a lot of people have already commented that, as usual, we're learning a lot more from you than we ever expect in one small period of time. So thank you.
Thank you.
I think while we're just waiting for a few more questions to come through, and it's funny because I did statistics as well, and seeing how you apply it for performance testing is really awesome. Can you, I don't suppose, give us another anecdote or two where doing measurement of computer performance tests, particularly where multiple measurements gave a really different variance for a reason unexpected? Mm-hmm. Just the importance of that multiple testing.
Oh, yeah. Even just trying to reproduce the results I had here with the kill became really hard to reproduce. And it turned out that the auto update had changed my kernel underneath me, which made it crazy. But yeah, there's lots of examples of that. One thing I found when I was doing the microstate accounting patches 10 years ago now, was that performance management and battery management would get in your way. So you'd get different results depending on whether you had your power plugged in or not, if you're using a laptop. Mm-hmm. I was measuring and there was a power cut and I didn't notice. And when I came back to it, there were a whole heap of results that just did not look right. There were more than 2 standard deviations from the mean. And so I thought, what's going on here? And I had to do them all again. And those ones were complicated because they took like half an hour each to do.
Have you seen anyone do, because so much of those event logs, so much of those changes are captured by system logs, right? System event logs.
Yep.
Is there anything useful in using machine learning or AI to actually monitor for correlation between events and change?
There probably is. But what I'm more concerned about is trying to get a consistent benchmark on every commit, if we can, to say this commit actually makes things worse, or this commit makes things better. Yep. But to do that, what we really need, and we haven't got this yet, I don't think, is a set of microbenchmarks that measure the key parameters inside the Linux kernel that people actually care about. So things like poll performance is crucial for web services. When the changes for Meltdown and Spectre went into the kernel, poll performance went through the floor because it has a switch statement that calls via a function pointer to do different things depending on which variable's being watched. And just replacing those, because there's only a few of them, with a comparison with the function pointer and then calling the function pointer directly, so you avoid the meltdown vector line stuff. Put the performance back where it should have been. But we should have noticed it and fixed it before we did it. So, yeah.
It's an interesting point, isn't it, that any release, that there's not actually a baseline that's associated with any any individual release. So maybe there's something there explicitly for the community to try to fix. If there was actually a baselining part, just another set of libraries effectively that are being updated each release, then everyone's baselines to actually test against. We've got a few extra questions from the group, and you should also know that there was a lot of applause in the Venulus chat.
Okay, cool.
Question: would it be valuable to have a microbenchmark suite, which is what we were just saying, that included more statistical knowledge? It did the repeat measurements for you, analyze the error and significance, etc.
Yeah, it would be valuable, but one of the issues is that you really need to reboot between tests to get a clean start, and that's hard.
Indeed, but a common suite that can be shared across the community, though, so at least people are testing against.
Yeah. That would be really good. And there've been people who are trying to do that, but none of them have really become mainstream yet that I know about. There may be some.
Okay. If the U-test is comparing who wins in between individual samples, does that mean the order of values in the test runs matter? Can you reshuffle the order of values instead of doing another run?
The only thing is really important is that the measurements are independent. So it doesn't matter what the order is, because you'll still get the same number of wins, draws, and loses, no matter what the order is. Okay. You can't just reshuffle the order of values, because that's going to give you the same result.
If they're measuring the same thing, if it's a measuring, yeah, okay, yep.
Yeah.
I guess I'm thinking, so one of the question says, I guess I'm thinking about bisecting something to figure out which commit tanked performance. Not sure what the usual thing to use there is.
It depends on exactly what you're trying to do. It's because in the kernel you've got to do a reboot anyway. You tend to run these things manually in single user mode and not come up to your normal GUI and desktop environment. So you've still got to build your kernel, install it, reboot, do the test, then boot back into a user mode and carry on. The easiest way is to have a separate machine just for doing the benchmarking, and set that up with a Ramphus that just runs your tests, and boot that by a PXE or something. That way works best.
Okay, wonderful.
Does that help?
So I think so. That's people's responding quite well to that. What would, if we were to try to get some consistency across the dev community in this, what do you think would be the most helpful things to set up?
I think first we need to know what we're measuring and what we want to measure. So finding out which functions are most important in the kernel, because some of them you only use every now and then, and they don't affect performance that much. But things like poll in Apache or Nginx, you really care about. So pick a few important applications, Postgres, Apache, whatever. Do some tracing to work out which functions are called a lot and have most influence on overall performance, and then generate a standard set of microbenchmarks for those, and just have a repository somewhere that's got all those. There have been a couple of academic attempts at doing this, but no one has really pushed them or published them to make them really available. And there are organized like Phoronix who are trying to benchmark Linux kernel, but they just do full systems benchmarks. So you can't actually very easily drill down and say it was this change or this function that's the problem. So maybe talk to the people at Phoronix and get some micro benchmarks added. I don't know.
Do you think that maybe there's a slightly different culture almost in the skill sets of developers in the either in private sector or non-profit or government potentially, and academic developers, because developers who are more in the academic field tend to be able to bring some of these disciplines in as their normal process.
That's definitely true. And if you're going to get a paper published in a top venue, you're going to have figures that are meaningful and figures that are backed up with decent statistics.
Yep.
One other statistical nasty that I wanted to bring up but didn't really fit with the talk is people comparing whether something is better than other just by taking the ratio of the means. The mean of the ratio is not the same as the ratio of the means. And what you really need to do is do a pairing of all the samples you've got for the before and all the samples for all the ones after. Find the ratios and then find the mean of that to get the expected value of before versus after.
Can you give us an example of where the difference? Yeah.
It's called Johansson's inequality. And one of the ones I've been screaming about recently is the effectiveness of masks studies that have been coming up on the COVID chats, because a number of them have been doing exactly that. They've been doing some sampling and taking the ratio of the means rather than doing the mean of the ratios, and the actual effectiveness is somewhat less than they're measuring.
Right.
It's still effective. Still keep wearing your masks.
Yeah, please. So we've got another question for you. If rebooting is recommended anyway, would making a live CD, live USB geared for microbench be helpful? And maybe something everyone could reuse?
No, it's not. Because a live CD has got the kernel built in. And what you want to be able to do is keep changing the kernel, because that's what you're benchmarking. At least that's what I'm benchmarking. If you're not benchmarking that, then maybe your mileage may vary. What I found it easiest is to use NetBoot and a PXE type system. So you boot via DHCP, because then you can automate the whole thing. You can just dump your kernel and your net Ramphus on a TFTP server, hit the button, and the benchmark runs.
Wonderful.
In fact, you can automate that if you've got a network controlled relay to do the rebooting.
Yeah, and Simon Fowler actually made a similar comment in the chat about PXE booting into test environments would allow you to have separate build systems. Indeed.
And that's what we do.
Wonderful. Look, we're a few minutes ahead of schedule. So, Peter, I know you've always got lots of good examples and stories to share. So I'm actually just going to invite, if you want to take a few more minutes to expand on any examples or to encourage folk to look at how they could actually build better testing into their performance work. Would you like to take a few more minutes?
I'm happy not to.
Oh, okay.
I do think that the U-test is really, really simple, because you can write an awk script in about 20 lines that will generate it for you. And will also give you mean and standard deviation and mode and all those things. And so it's trivial. I haven't bothered sharing it because it is so trivial.
Might be helpful to share for a couple of folk just to get them started, though. So would you mind sharing that? Yeah, cool.
Yeah, righto. I'll stick it up somewhere.
Okay, thank you so much. Well, for everyone else then, what we'll do is there's the Blemmings Labs post-talk Q&A channel. Peter, when you've got that somewhere, would you mind just dropping a link in there, folk? And if anyone's got any further questions, I might ask you to engage with folk on that channel so that they can just get any other questions out of the systems, or have a chat, or ask you for any samples or examples that they could use. And we might leave it there then. So thank you so much, Peter. As always, everyone learns a lot. Really appreciate it.
And thank you, Pia.
Oh, of course.